You ever just stare at a line of code and wonder, how does a computer actually turn that into something real? How does it go from what looks like a math equation to a functioning app? Well, it's not magic. So let's peel back the layers and see exactly how a computer learns to think in code. We're going to use this single line of code as our guide. It looks pretty simple, right? Familiar? But the journey this one statement takes from your keyboard to the computer's processor is honestly fascinating. Let's follow it and unlock the whole process. So, for real, how does it happen? It's a precise step-by-step process. There's zero room for guesswork. Let's trace our line of code as it goes through this journey piece by piece. Okay, so the very first thing a computer has to do is stop seeing our code as just a long string of characters. It needs to chop it up into meaningful chunks. Kind of like how you have to see individual words before you can understand a sentence. You can think of this whole thing like a factory assembly line for our code. The official name for it is compilation. We're starting right at the beginning at a station called the lexical analyzer. Its one and only job is to scan the code and group all those individual characters into useful clumps. This first step is called lexical analysis, and it's really all about two key ideas: lexemes and tokens. A lexeme is the actual text itself, like the variable name, result, or just a plus sign. But a token is the category of that text. The computer is essentially putting a label on everything, saying, okay, this thing is a variable name, this one's an addition operator, this one's for assignment. And here's what that actually looks like. Our simple code gets turned into this nice structured list. On the right, you've got the raw text, the lexemes we talked about. And on the left, you've got the tokens, the computer's internal labels for everything. So it no longer sees the letters RESULT. It sees an identifier whose name happens to be result. This is such a crucial first step toward real understanding. So now we have our categorized words. But just knowing what the words are isn't enough, right? You also need to know how they can be put together correctly. You need to understand the rules of the sentence. And in programming, that means understanding the language's grammar. That rulebook is called syntax. Every single programming language has one. Just like English or Spanish has a grammar. It's the blueprint that says, hey, an equal sign has to have a variable on its left and some kind of expression on its right. If you break these rules, the program is just plain wrong, and the computer knows it instantly. But wait, how do you write down these rules for a computer? You can't just write them in English. It's way too vague. So you need a special language for describing other languages. Think of it like a rulebook for how to write rulebooks. We call this a meta-language. One of the most common meta-languages for this is called Backus-Naur form, or BNF. Now, that rule on the left might look a little cryptic, but it's doing the exact same job as the English grammar rule we all learned in school. All it's saying is, an assignment statement is defined as an identifier, followed by an equal sign, followed by an expression. It's just a super precise, unambiguous way to lay out the structure of the language. Okay, so the computer has its tokens, the words, and it has the grammar, the rulebook. What's next? Well, it has to put them together. It has to check if our specific combination of tokens actually follows the rules from the grammar. This whole process is called parsing. So how does it do that check? It tries to build our line of code using only the official grammar rules. This is called a derivation. It starts with a big general concept like program, and then it applies one rule after another, breaking it down into smaller and smaller pieces. The whole goal is to see if it can end up with the exact sequence of tokens that we gave it. It's basically trying to prove that our sentence is valid by constructing it from the ground up. And the final result of that whole process is this beautiful thing, a parse tree. This tree is the computer's true understanding of our code. It's like a sentence diagram, but for programming. It's not a flat line of text anymore, it's a hierarchy. And the structure of the tree itself tells the computer the order of operations. It knows it has to calculate A plus C first because that's on a lower branch. Then it multiplies by B, and finally it assigns the whole result to A. The visual structure is the meaning. So why get into all this technical detail? Why does any of this matter? Because this entire process, from tokens to parse trees, is the absolute foundation that every single programming language is built on. Understanding this is the key to understanding why languages are designed the way they are. None of this is an accident. It is all meticulously engineered. See, every person who designs a programming language is constantly trying to balance these things.
the syntax, those grammar rules we just looked at, has a huge impact on everything. A language with a really simple grammar might be super readable, but maybe not as powerful. A more complex grammar could let you write amazing things, but maybe it's less reliable and harder to learn. A clear, unambiguous grammar is always the goal, because it makes it easier for both us humans and the computer to understand what the code is really supposed to do. And you know what's really wild? Language design isn't just some abstract concept. It's deeply tied to the physical computer hardware. For decades, most computers have used what's called the von Neumann architecture. All that means is the brain, the CPU, is separate from the memory. Now think about what that implies. It means the computer is constantly fetching data from memory, doing something to it in the CPU, and then putting it back. That physical reality directly led to the kinds of programming languages we use today, languages built around variables, which are just names for slots in memory, and assignment statements, which are just instructions for moving data around. Our code's very structure mirrors the machine it runs on.
And all of this brings us to the fundamental trade-off, the big question at the heart of it all. If you were designing a language from scratch, what would you choose? Do you make it easy and comfortable for the human programmer to read and write? Or do you make it as powerful and efficient as possible by sticking as close as you can to the raw hardware? There is no single right answer. And that fundamental tension is exactly why we have thousands of different programming languages today.